Welcome back to the course on architecture design of ICs. So, here we are continuing with the efficient architecture design from the algorithm, different algorithm, how efficiently we can implement the architecture, different architecture. There are different styles of implementation, that means the architecture will be different if we are considering for this speed efficient or power as a major constant or area as a major constant. So, the architecture will be different for the same algorithm, okay, or for the same function I will have or we will have different architecture for different perspective. Okay. So, that we are seeing in the last few classes, and we will continue more onto the same flow. So, in the last class what we are discussing about the circuit which can implement the GCD of two numbers. Okay. So, we have built the circuit, the basic components of the circuit we have already built. So, now we will try to find out the final architecture which will give me the GCD of two numbers. Okay. So, then again come back to the, that means, so here in the last few class, that means last class what we are seeing, that we have built this M registers and N registers, and then how we can build this M and N, that also we have seen. And now next is that again if we, that means we have already drawn or we have already defined the corresponding, this was the M registers and this was the N registers, right. Okay. So, if this is a Q I, this is C 1 I, this is Q I plus 1 and this is Q next, this is also Q I, this is C 2 I, this is Q I plus 1, this is Q next, and this is for M value and this is for N value. That means, here I am mentioning Qi, Qi means that is the value for Qm, that is not value for, that means this Qi and this Qi is not same. This is the, that means same input which will connected to the output for N values, and this is the same output and input will be connected for M values. Okay. So, that means this Qi and this Qi or this Q next and this Q next is not same. This is for M and this is for N. Okay. And what was the, that means control signal? The control signal was I need LSB of M and LSB of N. So, here also the same thing, I need LSB of M and LSB of N. So, we have already in the last class we have already developed this circuit for this C 1 and C 2, that also we have already developed. Now, we have to build the final architecture. So, I need these two. Basically, what was the logic? That means, whenever we are finding out the GCD using this particular algorithm, so at that time the final results how it will be? It will be x into 2 to the power n. So, where n is what? Whenever we find out this even positions for m and n, sorry m and n. So, at that time that has to store somewhere, and that information will come, and whenever this, that means what is the terminating condition for this? That means, whenever m and n value is same, at that time this loop will terminate. So, that means I need one this comparator block equals to comparator block, which says that okay, this m and n both are same. So, now computation will be over. Okay. So, that means I need one register where this will indicate, okay. So, this is the output, final output. So, this will indicate this registers that okay, you produce the result at the output bit. But at that time, whatever is the value of whenever this is m and n, so at that time that is the end point. So, now that value, with that value I have to multiply with this, that means how many times I find out this even position. So, even position, how can I determine that okay, these are the even position? That means when LSB of m and LSB of n both are 0 0. So, I need one NOR gate where this is LSB of m and this is LSB of n, which will give me that okay, this is the position where I am finding out these both as 0. So, this will be connected to where? This will be connected to a counter. So, that means whenever how many times I am finding this during these iterations, how many times I am finding this even, that will be recorded via this LSB m and LSB of n. So, LSB of m and LSB of n means okay, that we will explain with the example later. So, here basically this is one n registers. Okay. So, now that will be connected with what? That will be connected to a shifter, and this shifter value is coming with this, and this shifter output will be connected to this. That means, this is the load. So, what is the output of this? Why I need this shifter? I need to implement this particular function, that x into 2 to the power of n. So, that means, this is my x, this is the, that means terminating values, and that is to multiply it with how many times I am finding this even position. Okay. So, now if I just want to explain with the corresponding that means example. So, if I consider this 20 and 30 case, so what was the expression? So, 2, here it was 10 and then it was 15, then it was 2, it was 5 and it was 15, then it was 5 and then it was 10, then again I have to, that means in the next it was 5 and it was 5. So, both are same. So, this is 5. Okay. So, that means here only for this particular position I am getting this both are even. So, that means 2 into this is the, that means terminating condition. So, 2 into 5. So, the GCD of this 20 and 30, that it has to be 10. So, now you check whether this circuit is giving me the same results or not. So, in this particular case, this 20 and 30 is loaded over here. Okay. So, based on that, this LSB m and LSB n, where for these two it is 0 and 0. Okay. So, now then you see this is 1. So, this has incremented by 1. So, that means now this counter value has been incremented by 1. Okay. Then in the next, it is this next value is again comes over here. So, the newer value of m and n, this is m value is that means even and n value is odd. So, from here based on this will be now the corresponding value will be loaded to this, that means initially the value was 20 and 30, we have stored this, then this value is 10 and this value is 15. So, it will check whether that 10 and 15 both are same, no. Okay. So, that means this signal is 0 at that time. So, that means the register will not produce at the output. So, then what will happen? This particular case, so whether this LSB m and LSB n is getting the newer, that means incremented by 1s, it found that okay, this is not 0 0, that means this is 0, this is 1. So, that means this operation is not at all performed at that cycle. So, again then what will happen? 10 and 15 case, for this 10 and 15 case, for this 0 and 1, for 0 and 1 here, what will happen? It will try to select, it will do this m value by 5 and n will remain same. So, then again it finds that in the next cycle what will happen? It finds that it is 1 and 1, that means both are odd. So, for both are odd, this will not change. Is 5 and 15 is same? No, that means this particular operation will not performed. Only at that time what will happen? Again, as this is 1 and 1 case, so this will choose this C1i and this will choose C2i. So, C1i and C2i what will happen? This will choose minimum of this, which is 15 and 5, which is minimum of this is 5, and this is mod of m minus n, that is 10. Okay. So, then again in the next cycle what will happen? Again this will, this is even, this is odd, this is even, right. So, whenever this is even, that means it will be divided by 2 and m will remain same. So, that means m will remain same and this will be divided by 2 means this will be 5. So, and again as this is not even, so this will not happen, and 5 and 10 is not same. So, again this will not happen. So, once I reach to this 5 and 5, so at that time what will happen? 5 and 5 means this is 1. Okay. So, 1 and at that time this is 5, this is 5, that means at this particular position this is 5, this is 5. So, 5 into 2, here only one, this counter has been increased by only 1 times. So, that means from here it will 5 which will be multiplied with 2, that means then at that time it will be, this results will be 10 and it will produce the output as 10. The same thing will happen if I consider that as 40 and 60, at that time what will happen? 2 times I will find even case, for 40 and 60 it will be even, for 20 and 30 it will be even. So, that means for 2 times at that time this counter value this will be 2. So, that means 5 into 4, that means it will be 20. So, that means the GCD of this 40 and 60, that is 20, and I will get the 20 at that time as the output. Okay. So, this is the circuit which gives me the GCD of 2 numbers. Okay. So, now from this particular circuit, okay, we know that this is the GCD, means the greatest common divisor among 2 numbers. If you just see the LCM, which is the lowest common multiplication factor. So, can I, that means try to say that okay, that number also using this particular circuit can I implement? If I have a try, can I, that means the logic if I find out, can I do that? So, here if you see in each of this function, whenever I am getting this, the LCM of this, if I just go to this, then 20 and 30 if I consider. So, initially what that is 10 and sorry. So, 20 and 30, that means here it is 10, it is 15. So, that means here I am doing 2. So, then this is 5 and this is 15. So, here I am doing 2, then this is 5 and 10, that means here if 2 divided by 2. So, that means 5 and 5. So, here from here if I get 5. So, that means 2 into 2 into 2 into 5, what is that? 5 into 8, that is 40. So, using this particular circuit I cannot implement the LCM of that. If I want to calculate the LCM of this, at that time I have to follow or I have to design another algorithm to find out the LCM. And then how can I do? Because LCM means what? LCM means what? The product of m and n divided by the GCD. So, that means how can I find out the LCM from this particular circuit? I am having this GCD circuit, right, where I am putting this m and n. I need another particular multiplication operation if I produce one divider circuit over here, which gives me this m and n divided by this GCD. So, at that time I can find out the LCM of m and n. Okay, understood? That means, now I need from this particular GCD function, I can, that means this I have to start with this GCD, then I can find out the LCM 2 by using this particular logic. Okay. So, this is the, that means, this is we have to start from the basic, then from the basic now we can try to keep on building the cell. Okay. So, this is that means the implementation of GCD function, and whenever you are following this course, at that time please actually let me know if you are having, that means any of the circuit, that means or for this particular system. So, it is your thought how you basically how you think that if I implement in this way, so I can get actually it depends upon your requirement, that means whether you are choosing speed as a constant or power as a constant or area as a constant, right. It is not at all true that whatever circuit, or actually here I am showing you the different implementation style for different application. Okay. So, whenever you are following this course, at that time if you find or if you are having any problem related to your research or your that means your design, okay, any type of circuit doubts if you are having, at that time please let me know in the forum. Okay. So, you just post that question on the forum, obviously I will try my level best to solve that problem. Okay. So, then again continue with the course. The next circuit which I want to implement, that is, let us consider I want a function which will give me this. Okay. So, what I said in the, that means we have to implement this kind of function, right, x into 2 to the power of n. So, if I want to that means implement this kind of architecture, that means I want a function which will give me this x into 2 to the power of n. So, what will be the circuit for this? So, then what I need? Basically this 2 to the power n means what? That is the multiplication operation of x. That means how, if n value is 0, that means 1. So, if it is x. If n value equals to 1, so that means this is x square, sorry 2x. If it is 2, so that means at that time it is 4x. So, that means 2x, 4x, 8x means what? I am just putting or adding zeros at the end of these x values. Whenever we are dividing, So, x if I just that means divide by 2 to the power n, that means I am discarding the LSB position, and whenever we are multiplying with 2 to the power n, at that time it means what? I am adding zeros at the LSB position to increase the, as this is binary weighted values. So, that is why we are increasing the value by putting extra zeros to the LSB position. Okay. So, for this particular function, for implementing, what I require is that I require 1 bit control shift operation. So, 1 bit control shift operation means what? I need 2:1 multiplexers. So, if I consider suppose this x input, x is the input of 16 bit, let us consider that, and I need 1 bit control shift of that. So, at the time what will be? So, that means here it will be up to x to the power 14, x to the power 50, x 15, x 13, x 14, x 12, x 13, here it will be 0 and it will be x 0. Okay. So, now this each of these will be connected something like this. This is the select line or S0 if I say. So, this is, that means this is 2:1, 2:1 marks. So, this is the marks. Okay. So, this is 1 bit control shift operation. If I want it 2 bit, so at that time only the bit position will change, right. So, how the bit position will change? So, if I consider 2 at this particular stage, so if I consider this as a select line at that time, each of this is marks, 2:1 marks. So, at that time what will happen? This will be x 13, x 15, this will be x 12, x 14, this will be x 11, x 13, this will be 0, x 1, 0, x 0, okay. And this is for x 1. Okay. So, that means whenever I need 2 bit shift, at that time these 2 zeros will be padded to the LSB position. So, the same thing if I need 4 bit control shift operation. So, at that time 4 zeros will be added. For 8 bit operation I need this kind of, that means a up to, that means 8 LSB position will be padded with 0. So, now if I, that means if I just, this is for 1 bit, 2 bit, sorry 1 bit, 2 bit, 4 bit and 8 bit. If I need, let us consider 5 bit. So, at that time how can I do? I can, if I just implement it in a structured way. So, at that time I can do it any values of this control shift operation. How can do that? So, if I just add it something like this, if this is my x, so this is my x, this is let us say S3, this is S2, this is S1, and this is S0. So, this is let us consider 8 bit control shift, this is 4 bit control shift, this is 2 bit control shift, this is 1 bit controlled shift. So, if you just put this value to, that means if you just change this corresponding bit values to this select line, then you will get that number of that means shift operation of the x input. How? If you just select this as 1, this as 1 and this as 1 and this as 0. So, at that time how many shift you require, you will get in terms of this x this time, as this is 0, that means there will be no shift at this particular stage. So, x will be coming over here. So, here it is shifted by 4, that means initially this x is shifted by 4. Then again that value will be shifted by 1, means it will be shifted by 2. Then again that value will come here and that will be shifted by 1. So, that means total 7 bit shift I will get of x, or 7 bit x shift means that is x into 2 to the power of 7. Okay. So, if I need, so that means n value is, if it is of 4 bit, so that means total 15, from 0 to 15 I can choose any value of shifting of this x. So, by this structured manner I can shift within this any values of this within the range of 0 to 15. So, if I put that means 10, so at that time I have to select that as 0, here 1 0. So, that means here it will be shifted by 8 and here it will be, sorry, this is 8 plus 2. So, that means it is 2. So, here I will get 8, here I will get 2. So, total 10 bit shift means x into 2 to the power 10 I will get as the output of. So, this is the structured for, this is the architecture for x into 2 to the power n. Okay. So, thank you for today's class. Again we will see other circuit implementation technique in the next class. Thank you.